What Bohr and Heisenberg did was nothing less than to unleash a revolution which turned physics on its head. At the turn of the century, the concept of atoms was so controversial that some physicists said, bah, humbug, atoms don't exist. Then comes the Bohr-Heisenberg theory, and all of a sudden we can peer perhaps directly into the heart of the atom itself. We can decipher all its magical properties. The dance of electrons, the laws of chemistry were spilling out from the Bohr-Heisenberg theory. Quantum mechanics is perhaps the most successful theory of all time. And some people ask, well, what has quantum mechanics done for me lately? And the answer is, look around you. All the wonders of laser technology, modern computers, transistors, the internet, modern DNA research for that matter, all of that is a byproduct of quantum mechanics. But back in 1925, I think physicists were naive. For them, it was an intellectual exercise. It was for the curiosity's sake that they wanted to probe deep into the heart of the atom and the nucleus. They did not understand the forces that would be unleashed once they began to tamper with this nucleus. One Italian physicist, Enrico Fermi, working at Columbia University here in New York, did the calculations, did the experiments, and for the first time realized that you can unleash this devastating power on a modern city. And there was a window in his laboratory, and as he looked out the window and he saw the skyscrapers of New York City, he realized that perhaps everything he could see in New York would be reduced to nuclear ash with an atomic bomb. Before the work of Bohr and Heisenberg, we had this Newtonian theory, a beautiful theory introduced 300 years ago by Isaac Newton that basically says that the universe is made out of tiny little balls. If the atom were in some sense like a miniature solar system with tiny little steel balls going around a nucleus, they should be unstable. Imagine, for example, two atoms colliding. Electrons should fly apart and the atom should disintegrate within a millionth of a second. But atoms are stable. Atoms bump into other atoms. Atoms form molecules with other atoms. But we had a paradox. What kept the atom together? What kept the molecules together? When Bohr and Heisenberg introduced quantum mechanics, it brilliantly solved this whole paradox. Because the electron is neither here nor there, it's spread out, it's everywhere. So the very fact that molecules are stable is a byproduct of the fact that electrons in some sense can be two places at the same time. If we didn't have quantum mechanics, all physical reality would disintegrate. Albert Einstein was so upset by the work of Bohr and Heisenberg that he said that if he had known that his work on the quantum theory and the photon would lead to quantum mechanics, then he would have become a cobbler instead of a theoretical physicist. You know, Bohr once said that if you are not shocked by the quantum theory, you don't understand it. If I were an electron inside a modern computer, I would see a fantastic world. I would see a world where in principle electrons could be two places at the same time. Now imagine that quantum world being our world today, a world of trees, a world of rocks. You could be two places at the same time, you could disappear, reappear. There'd be a probability that fantastic events could become commonplace. Before the work of Bohr and Heisenberg, we believed in something called objective reality. What you see is what you get. The world of common sense is the actual world. Things exist in definite states. Then come Bohr and Heisenberg, who say, not so fast. Things are not what they really seem. Until you make an observation, you don't really know precisely the state of an object. Philosophers have asked that age-old question. If a tree falls in a forest and there's no one there to listen to it, did it really fall? Now come the quantum physicists. And they say that before an observation is made, that tree exists in all possible states. Perhaps that tree is really a sapling. Perhaps that tree is a full-blown tree. We don't really know. In fact, it's in the superposition, the sum of all possible states before an observation is made. This sounds bizarre. This sounds fantastic, but this is the most successful way of interpreting physical reality. There is a probability that tomorrow, when I wake up in the morning, I will wake up on the planet Mars. It's a very small probability, but it's there. It's this kind of uncertainty that dogs modern science even today. We ask the question, how can it be? How can it be that you can exist in a never-never land before an observation is made? So we have a many worlds theory. Perhaps there are alternate versions of myself existing in other universes. Perhaps I went to a different school. Perhaps I picked up another subject. Perhaps I got interested in something else and pursued an entirely different career. There are perhaps other worlds just as real as this one, in which physical reality played itself in an entirely different way. Quantum mechanics also gives us this bizarre phenomenon called entanglement. The idea that what happens on one can affect the other part of the universe instantly, faster than the speed of light. Well, of course, Albert Einstein didn't like this at all. Einstein said nothing can go faster than light. But here was a contradiction. Einstein was wrong. You can know something faster than the speed of light. We are entangled in a quantum web, that what happens in one part of the universe instantly affects another part of the universe. As they say, we are one. The universe is one gigantic cosmic web such that ripples here can instantly affect ripples on the other side of the universe. If Bohr and Heisenberg were still alive, I would ask, was it just intellectual curiosity which drove them to understand the laws of atomic physics, or did they really foresee the coming of modern electronics and modern medicine as well? If quantum mechanics is really correct, then perhaps we can have a theory of everything. Perhaps an equation no more than half an inch-long equation, which, inserted into the Bohr-Heisenberg theory, would give us the enormous diversity, this fantastic wonderment that we call our universe. In other words, the Bohr-Heisenberg theory may give us the foundation by which, one day, we may be able to read the mind of God.